So now we're going to focus on these binomial experiments. And we're going to want to calculate probabilities. And so our general question for a binomial probability is going to be, now this is generic, what's the probability of getting a certain number of successes out of a certain number of trials? So if I shoot 3 free throws, what's the probability that I'm going to make 2 of the 3 free throws? That's a binomial probability. What's the probability I'm going to make 1 of the 3 free throws? What's the probability I'm going to make 2 or less of the 3 free throws? Those are all binomial probability questions. So it's going to be a certain number of successes out of a certain number of trials. So I'm going to set this all up on how we go about calculating these probabilities. So I have a scenario for you. Suppose that I decide to be mean and I decide to give you a pop quiz. So suppose I decide to give you a pop quiz and I'm so mean, I'm going to give you a pop quiz over material we haven't studied yet. The quiz is going to consist of 3 multiple choice questions, each of which has 5 answers from which you must pick the 1 correct answer. So the 5 answers are A, B, C, D, or E. So you're picking 1 correct answer out of 5. Since we've not studied the material yet, you have to guess. So my question for you really is, what's the probability that you won't get any of them right? What's the probability you'll get 1 question right? What's the probability you'll get 2 questions right? What's the probability you'll get all 3 questions right if you're guessing? So this is a binomial because there's 3 trials. You have 3 questions. Because there's 5 choices that you have to pick from, you have a 1 out of 5, 1/5 probability of guessing a question correct. And that means you have a 4 out of 5 probability of guessing a question wrongly. That's going to be the same for all 3 problems. So that probability is fixed. Whether you guess correctly for the first question is independent of whether you guess correctly for the second problem, and that's independent from whether you guess correctly on the third question, and so on. So this is a binomial scenario. So if success is answering a question correctly and failure is answering a question incorrectly, then n equals 3, p equals 0.2, that's 1 divided by 5, and 1 minus p equals 0.8, that's 4 divided by 5, or 1 minus 0.2. So my first thing that I want you to do is I want you to list the sample space for this probability experiment and calculate the probability of each outcome. So the sample space means I literally want a list of all the possible outcomes that could occur. So again, success is answering correctly, failure is answering incorrectly. So my sample space is going to be this. For the first problem, I could answer it correctly, so that would be success. For the second problem, I could answer correctly. That would also be success. My third problem, I could answer correctly. That would also be success. So this is one possible outcome on my pop quiz. Now, I could also answer the first question correctly, the second question correctly, but I could miss the third question. So that's another possibility. So that's another item in my sample space. I could also guess the first question correctly, the second one incorrectly, and the third one correctly. That would be another possible outcome. Or success, failure, failure. That would be another possible outcome. I could guess the first question incorrectly, and then the second and third correctly. Or the first one incorrectly, the second one correctly, the third one incorrectly. Incorrect, incorrect, correct. Incorrect, incorrect, incorrect. These are the 8 possible outcomes that could occur on this quiz. This is the sample space. Now, can I calculate the probabilities? Well, the probability of me getting success would be what? Well, the probability of me guessing the first question and the second question and the third question correctly. First of all, I've already said the three questions are independent from each other. So I could calculate this probability by using the multiplication rule. The probability of guessing the first question correct is 0.2. The probability of guessing the second question correct is also 0.2. The probability of guessing the third question correct is also 0.2. So if I take 0.2 times 0.2 times 0.2, that's 0.008. So the probability of me guessing all three questions correct is 0.008. Which means if I gave this pop quiz to 1,000 students, about 8 would be able to guess all three questions correct. Now, what's the probability of getting the first two correct but missing the third one? Well, it's the same kind of deal. That would be 0.2 for the first, 0.2 for the second, but for the third, it would be 0.8. So getting the first one right, getting the second one right, getting the third one wrong would be 0.8. So if I take 0.2 times 0.2 times 0.8, that probability is 0.032. So again, if I gave this pop quiz to 1,000 students, about 32 of them would get the first two questions right and miss the third one, if they're just guessing. What's the probability of this third one? Success, failure, success. Well, the probability of getting the first one right is 0.2. Getting the second one wrong is 0.8. Getting the third one right is 0.2. So can you see 0.2 times 0.8 times 0.2? That's going to be the same result, 0.032. So if I, again, gave this pop quiz to 1,000 students, about 32 would get the first one right, the second one wrong, and the third one right. The probability of first one right and the next two wrong, 0.2 times 0.8 times 0.8. So 0.2 times 0.8 times 0.8, that would be 0.128. So again, if I gave this quiz to 1,000 students, about 128 of them would get the first question right and then miss the second and third questions. Probability of getting the first one wrong, then getting the second and third ones right. Well, getting the first one wrong is 0.8. Getting the second one right is 0.2. Getting the third one right is 0.2. And 0.8 times 0.2 times 0.2 is going to be 0.032 again. Probability of getting the first one wrong, the second one right, the third one wrong. That'd be 0.8 times 0.2 times 0.8. 0.8 times 0.2 times 0.8 would be 0.128 again. So again, if I gave this quiz to 1,000 students, 128 of them approximately would get the first one wrong, get the second one right, get the third one wrong. Probability of wrong, right would be 0.8 times 0.8 times 0.2. And so that would be 0.032. I'm sorry, 0.128 again. Let me fix that. So again, if I gave this to 1,000 students, about 128 of them would get the first two wrong and get the third one right. And last but not least, what's the probability of wrong? Well, that would be 0.8 times 0.8 times 0.8. And 0.8 times 0.8 times 0.8, that is 0.512. So if I gave this quiz to 1,000 students, about 512 of them would miss all 3 questions. So this is the sample space, right? So look at part B. Let X equal the number of questions answered correctly out of the 3 questions. Complete the probability distribution for the binomial experiment. So if I have 3 questions, then the number that you could possibly get correct would be none of them, 1 of them, 2 of them, or all 3 of them. And I want to calculate the probability of each of those outcomes. Now, the probability of getting none correct, the only way that can happen is this false, false, false scenario. This is getting none correct, 0 successes. And so that probability right there is 0.512. The probability of getting 1 question correct, well, that can happen 3 different ways. If you look, right here we have 1 question correct, right here we have 1 question correct, and right here we have 1 question correct. So getting 1 correct could be success, failure, 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 success, failure, or failure, failure, success. It could be any of those 3 things. Now notice something. Notice what the probabilities are for each of those. They're all the same, 0.128. So for this probability, I'm going to add 0.128 plus 0.128 plus 0.128, or in other words, multiply by 3. So if I take 3 times 0.128, that probability is 0.384. So the probability that the student will guess 1 question correct is 0.384. What's the probability that we'll get 2 correct? Well, again, there are 3 ways that that can happen. We can have 2 correct here, 2 correct here, or 2 correct here. So the first 2 right, third one wrong, first one right, second one wrong, third one right, first one wrong, and the last 2 right. So there's 3 different ways that I can have 2 successes. And notice those probabilities, 0.032, 0.032, 0.032. So the probability of 2 successes is going to be 0.032, 0.032, 0.032 added up. If I take 0.032 times 3, in other words, 3 times 0.032 is 0.096. So that is the probability of guessing 2 questions correct. And the probability of getting all 3 correct, that can only happen this one way, success, 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 and that probability is 0.008. This is the binomial questions. We figure out the probabilities like this. So the question is going to be, what's the probability of 0 successes, 1 success, 2 success, or 3 success? And we can figure those out because we have the multiplication and addition rules. So again, interpretation, if I gave this quiz, this pop quiz to 1,000 students, 512 would get none of the questions right, approximately. 384 would get 1 question right, so they'd make a 33%. 96 would get 2 questions right, so they'd make a 67%. 8 would get all 3 questions right, so they'd make 100%, strictly by guessing. So what I want to examine is how maybe I could calculate this a little more easily without having to literally list all of this. So like, for example, I'm not likely to give you a quiz that would only have 3 questions on it. If I was going to give you a pop quiz, it'd probably have more like 5 questions on it or 10 questions on it. Well, the trouble with that is if I give you a quiz with 5 questions on it, then the sample space is a lot larger. I could have success, 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 or success, 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 failure. or success, 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 failure, success, and so on through failure, 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 failure. We would have 2 to the 5th power. 2 to the 5th power would be 32. There would be 32 different possibilities in my sample space that I would have to do this for. That's kind of challenging. If I had 10 questions, there would be 1,024 different outcomes possible, and that would be more challenging to list all the possibilities. So let's look at the pattern of what's going on. So if you take a look at this first probability here, when we had success, 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 what happened there in order to calculate that is we got 0.2 3 times. When we had success, success, failure, we had 0.2 twice, and we had 0.8 once. Success, failure, success, we had 0.2 twice, and we had 0.8 once. Success, failure, failure, we had 0.2 once, and we had 0.8 twice. Failure, success, success, we had 0.2 twice, and we had 0.8 once. Failure, success, failure, we had 0.2 once and 0.8 twice. Failure, failure, success, we had 0.2 once and we had 0.8 twice. And failure, 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 we had 0.8 3 times. Well, think about this. When we had all 3 successes, then we had 3 successes. So the probability of success ended up occurring 3 times. So that's like to the 3rd power. We had 0 failures. So 0.8 occurred 0 times. So I can calculate this probability by taking 0.2 to the 3rd times 0.8 to the 0, and that equals 0.008. Here, I had 0.2 twice and 0.8 once. So I could calculate this probability by taking 0.2 and squaring it times 0.8 to the 1. So I had 2 successes and 1 failure. So I had 2 0.2s and 1 0.8. Same here, 2 successes and 1 failure, 0.2 squared, 0.8 once. Here I had 1 success and 2 failures. So 0.2s once, 0.8 twice. 2 successes, 1 failure, so 0.2 twice, 0.8 once. 1 success, 2 failures. 1 success, 2 failures. Here, all 3 failures, so we had 0.2 0 times. So if I had 10 trials, and let's say I had 6 successes, 10 trials, 6 successes. Well, if I have 6 successes, I have 4 failures. So I would calculate the probability by taking 0.2 to the 6th because there were 6 successes, and 0.8 to the 4th because there's 4 failures. Now, the other part of this is how many different ways can I have all successes? How many different ways can I have 1 success? How many different ways can I have 2 successes? How many different ways can I have all 3 successes? Well, if you look at that, all 3 successes, that can only occur one way, right there. How many ways can we have 2 successes? Well, that could occur 3 ways, right there, and right there. There were 3 ways. Now, get this. If I have 3 trials, how many ways can I have 2 successes? That would be a combination. 3 trials, 2 successes. And if you do that on your calculator or by hand, whichever way you want to do it, but like 3 math, probability, choose 2, that's 3. So there's 3 different ways that I can have 2 successes out of 3 trials. How many different ways can I have 1 success? Well, that happened here and here and here. So there were 3 ways that I could get 1 success. That is 3, choose 1. If you do that, 3, choose 1, that is 3. How many different ways can I have all 3 successes? The only way that happened was right here. That is 3, choose 3. And if you do that, 3, choose 3, that can only happen one way. And incidentally, I didn't do it up here, but if I have 3, choose 0, So that's 3 trials, 0 successes. That is 1 as well. Actually, that's what I should have been doing here. 3 choose 0 should have been what I did here. That's 1. 3 choose 3 is also 1. That's all 3 successes right here. So this leads us to a shortcut. It leads us to a formula for being able to compute these probabilities. So that's what I was setting up. I'm explaining why this formula works. So the probability of obtaining X successes in N independent trials of a binomial experiment is given by P of X equals a combination. So we're going to take N combination and we're choosing X. So N's the number of trials, X is the number of successes. So it's the combination of N choosing the number of successes times. Then the probability of success is going to be raised to the number of successes power. And then the 1 minus P, that's the probability of failure, is going to be raised to the number of failures power. So if there are X successes and N trials, then there would be N minus X failures. So again, like if I have 10 trials and if there's 6 successes, then there would be 4 failures. 10 minus 6, 4 failures.